Okay, so welcome to this next video in linear programming. The previous video we were talking about the simplex algorithm being formalized, and we did that by iterating it on a general instance of a linear program. One thing we mentioned, of course, was that we needed a basic feasible solution to be the catalyst of that entire process. And but typically when you're just in practice, if you have a linear program, you're not going to have an associated basic feasible solution. And so that's what phase one of the simplex method is for. It starts from scratch with just the linear program, and then you're supposed to get a basic feasible solution from that. So here is roughly how phase one works. You start with your linear program, the original one, and then you're going to construct an auxiliary linear program, so it's related to the original. And by construction, it's very easy to get a basic feasible solution of this linear program, and then you can run the simplex algorithm on it to get an optimal solution. It will be optimal by construction. And once you have an optimal solution of this auxiliary, that's going to correspond to information about the original linear program that this auxiliary was derived from. And there's two possibilities. Either the information you get from your optimal solution will tell you that the original linear program is infeasible, or it will give you an explicit feasible solution for your original linear program. So if it's infeasible, you find out that the original is infeasible, then you're just done, because of course there's no optimal solution for the simplex algorithm to find for the original. That's because there's no solutions at all. And on the other hand, if you have a basic feasible solution, if you just have a feasible solution, then there's just it's a fact that if you have a linear program with a feasible solution, let me say that again. Any linear program with a feasible solution also has a basic feasible solution for some basis. And I put an asterisk there because that's actually a non-trivial implication. But what we're going to do in this video is we're just going to take it for granted that a feasible solution can, there's a way to go from a feasible solution to a basic feasible solution. So for the purposes of this video, we're just going to be trying to find a feasible solution and take this implication for granted. Now that we have but once you do have the basic feasible solution for the original, now you can use the phase two process, which is the part that we've already talked about, in order to find optimal solutions for your original linear program. And just one thing I wanted to point out is that we are using the phase two part within this auxiliary linear program. So phase two gets used inside of phase one, actually, but in a very particular way. Because in this auxiliary, you're automatically going to have a basic feasible solution. There's no work associated to that. So counterintuitive as the indexing numbering may seem, 1 and then 2, actually it's the correct logical progression of in terms of introducing these things to go in is 2 and then 1, because you need 2 inside of 1. Funny enough. So okay, so let's go through the details of that. So we're going to call P the original linear program that we start with. So typical formulation here. And with WLOG, that's without loss of generality, we're going to assume that this right-hand side vector B is a non-negative. And that's just because, well, you could say, well, what if there was a component that was negative? Well, for instance, here's the vector B, and here's a particular component BI, and let's say that component is negative. Then for this row that I've circled in green, well, that's just one individual linear constraint of all the constraints that you get from this A times X equals B matrix equation. And for that one particular constraint, just multiply both sides by -1. That'll flip this to be positive, and it'll just flip, negate all the coefficients of this row of the matrix A. But you're not changing any of the solutions. The x's, it's the same equation, right? You just multiply by -1. The x's that satisfied before still satisfy, and everything's fine. So just do that, and then so that means you can assume that it's non-negative. If it wasn't, you just multiply by -1 for a particular component that violates non-negativity. Okay, so that's what our assumption is, and here's our format. And it's not clear that this has any basic feasible solution. That's what we're trying to do, find a basic feasible solution. And so here's how you do it. You construct an auxiliary linear program which definitely has a basic feasible solution. And so P will be our original, and Q will be the auxiliary. So here's P up here, and here's Q, the auxiliary, and here's what it is. So I've just put a placeholder for the objective function for now. We'll address that in a moment, but for the constraints, you have this matrix of constraints, this matrix here, times y equals b. And so what the matrix is, it's the original matrix A from the original linear program, and then you append an identity matrix after that. And that's the overall matrix here. And then times your variable vector, that equals the right-hand side will still be the same vector b that it is above here. So the a is the same as above here, and the b is, of course, the same as above. That's obviously why we're using the same notation. And then just aesthetically, I just chose to call these variables y's rather than x's, mainly so that we can just associate y with being auxiliary, while x is associated to the original linear program P. And I mean that's just an arbitrary choice, but just for our own abilities to keep things straight, we'll do that. And then we also want that the y vector to be non-negative. So more explicitly, what is this matrix? What is it? This is just kind of compact notation, but it's, so you start off and you put the columns of the matrix A. So I mean, in other words, you put the matrix A, and it consists of these columns, A1 up to AN, and then that gives you A, and then you put the identity matrix, and you know, we want to construct this so that this makes sense. So all the dimensions have to fit together. So if A is conventionally considered to be m rows, so this is m here, number of rows. So we want the identity matrix to also have m rows, so it fits in line here, and so it's an identity matrix is square. So if it has m rows, it also has m columns, and so in total, this overall matrix has n plus m columns. Of course, the first n being the first n columns being the columns of A in order, and then the latter m columns being the identity matrix columns. Then that times y is the right-hand side vector b, consisting of those components. And okay, why is it easy to find a basic feasible solution? Well, it's quite clear. You exploit this identity matrix, and that automatically gives you a basic feasible solution. And what it is you take y, this basic feasible solution, to be, well, the first n components are all zeros, and then the latter m components are the components of b in order. And that works because, you know, if you take this overall matrix A appended by I and times it by this vector y, well, you'll see that all the components, so it's a linear combination of the columns, and the coefficients in front of the A columns are all zeros. That's the first n columns, so first n entries are zeros, so those just vanish, and then what you're left with is each individual component of B times an identity matrix column, and they come in order, and so then what you get is, because this is the identity matrix, you get that the overall thing is of course the vector B. So this works. So A appended by the identity matrix times this vector Y, of course, gives you the vector B because you have an identity matrix here, so you make this choice. So it's feasible, of course. It's basic feasible because it's for the basis corresponding to the columns of this identity matrix. So they come after the first n columns, so it starts at column n plus 1, then n plus 2, and on, up to n plus m. So those are the indices of the columns for this basis that this vector y is a basic feasible solution of. And yeah, so it satisfies the two criteria, as we've already explained. A appended by I times y is b, and then y is non-negative because each of the components are either zeros or they're the components of b, and we've already assumed above that the components of b are non-negative, and so that ensures that this is non-negative. And then of course it's basic feasible because you know the non-basic components. So the basic components are the 1, the m. The non-basic components are the first n, and they're all zeros. Excuse me. So those. So then obviously that's a basic feasible solution. So we get that by construction. So what we've done so far is by construction we have a basic feasible solution, but we haven't shown why it's useful yet. And so now we're going to figure out what the objective function should be so that this actually becomes useful. Okay, so here's the original linear program P again. I just wrote it just so we can have this direct comparison. And then here's the auxiliary Q. And then what the objective is going to be is you're going to minimize the sum of the final m components of that vector y. So yn plus 1 plus yn plus 2 plus all the way to yn plus m. So originally those components, we start off with the first basic feasible solution being these components, b1 to bm. And then your goal is to try to minimize those. And yeah, and by the way, just so we're on the same page, x's, there's n components because that corresponds to the number of columns of the matrix A, so, which is n columns. And then y's, there's n plus m components, and that's because there's n plus m columns of this matrix A appended by I. So I mean, that's just for all the dimensions to work out appropriately. Yeah, so we're trying to minimize this sum here. And one thing to note is that this auxiliary Q is feasible and it's bounded. So it's feasible because we have not only do we have a feasible solution, we have a basic feasible solution. And it's bounded because each of the components have to be non-negative, and we're trying to minimize this sum here. So at best, we're going to get zeros for each of these components. We don't know that we can get that, but that's the best we could hope for. And so that's a lower bound. 0 is a lower bound on this objective function. And so it's feasible and bounded. We have a basic feasible solution, so we can use the simplex algorithm. And by simplex algorithm, I mean phase 2, which is the phase that we've already discussed. And that will find us an optimal solution to Q. So it's not going to be, it'll never be the case that this is unbounded. We just said that it has to have a lower bound of 0. And so when we already have our basic feasible solution, so now we can run simplex and get an optimal one. And again, by construction, there was no work involved in finding that basic feasible solution. It just came automatically by the format here. And so that's what allows us to use phase 2, simplex algorithm. Okay, so what's the purpose of Q? So why did we construct this objective function to be what it is? And here is the point. The point is that we want to figure out something about the original linear program P. And here's what we figure out. So the original linear program P has a feasible solution if and only if the optimal value of that linear program Q, auxiliary, is 0. So 0, we said, was a lower bound. There's no way we're going to do better than that for Q, but in fact we have to attain exactly that if we're going to have a feasible solution. So if we do attain that, then we will have a feasible solution, and if we don't attain 0, then we will not have a feasible solution for P. Okay, so why is that? So take y star to be an optimal solution that you get from the simplex algorithm when you run it on Q, and then there's two situations. Either the objective value, which is, it's the sum of those components, the n plus 1 to n plus m components of y star, you add those together, and either what you get is 0 or it's going to be positive. So let's first deal with the case where it's 0. If it's 0, then that means, well, each of the individual components had to be non-negative, and if the sum ends up to be 0, then that means all of the components are exactly 0. And so what that means, and that's the components, the last m components. So what that means then is when you consider A appended by I, that matrix, times this y star. Well, on the one hand, y star is feasible amongst other things, so I get the vector B. And on the other hand, but also the components, the last m components are zeros, and those last m components are the components associated to the m columns of the identity matrix, and so they just vanish. And so what you're left with is the first n components being multiplied by the columns of A. And so that's what I'm writing here, A times y star sub n, where this brackets n subscript here. This is just indicating that this is the subvector of y star indexed by the first n components, because the last m of them are vanishing because they're zeros times the identity matrix columns. So this is an n-dimensional vector here. It's the subvector of y star, being the first n components. So what we have is an n-dimensional vector here, and A times it gives us B, and then of course the overall vector y star is non-negative. So in particular, the first n components are non-negative, and so that's enough for us to conclude that this subvector of y star is feasible for P. So it satisfies non-negativity and it satisfies the matrix constraints. A times it equals B. So this is feasible. So with and so that would all, as an aside, just by the way, that would also give us that P has some basic feasible solution because we have a feasible solution by that implication that we're assuming. But that's not relevant right now. Right now we're just showing that if we start off with our objective function value summing to give us exactly 0, then we get this an explicit feasible solution for the original vector P, program P. So it's feasible. Okay, and on the other hand, if that sum for the optimal value is positive, that's going to imply that P cannot be feasible. And basically that would be because if it were feasible, if P were feasible, then we'd be able to construct a solution for the auxiliary Q, which has an even better objective value, and by better I mean less, because we're trying to minimize. It's even better than this, but that would contradict the fact that this is supposed to be optimal, and so that means we can't have a feasible solution if this is positive. So yeah, let's in detail. If P did have a feasible solution, call that x hat, then what you can do is you can construct a solution to the auxiliary like this. You just take the components of y to be, well, the first n components are just the corresponding components of x hat, and then the last m components are all zeros, and that's feasible for Q because, well, just of course it is. A appended by the identity matrix times y. The last m components of y are zeros again, so the identity matrix columns will vanish when you take this linear combination of the columns, and then you're just left with just a times the first n components of y, but those components are the components of x hat, and so that's a times x hat, and we already know that that's b, so we have that a appended by I times y equals b, and so it satisfies that constraint. And then it's also non-negative because we're assuming x hat is feasible for P, and so it's non-negative, and then y consists of it, and then also zeros. So then y is also non-negative. And so it satisfies all the constraints, so we have a feasible solution y constructed like this. And then if you think about what the objective function is, it's the sum of the last m components, but that's the sum of all zeros, and so that would give us 0. But that's, of course, strictly less than what we're assuming the sum of y star n plus 1 plus y star n plus m is, and that's supposed to be optimal. So y star was supposed to give us the best possible, but we found a feasible solution y, which is even better than y star. And, of course, that's a contradiction with the fact that y star is optimal. So that's a contradiction, and so that must mean that P cannot have a feasible solution, because if it did, we could do this construction and contradict optimality. So what we have is that auxiliary Q. When we run Simplex, either we're going to find out that P is infeasible because our optimal value will be positive, or we'll get an explicit feasible solution for P. So and here's just that kind of written out strategy for getting a basic feasible solution of P. First, construct the auxiliary problem Q, and then get a basic feasible solution for it, which can always be done easily by the way we constructed Q. And then you can get an optimal solution for y star of Q by the phase 2 simplex method, because we have this basic feasible solution that we automatically got. And now that we have this optimal solution, we'll find that either the optimal value of Q is positive or it's 0. So if it's positive, then that means that P is infeasible, and we're done, because there's no feasible solutions to the program P that we care about. And then on the other hand, if the optimal value of Q is exactly 0, so we attain that lower bound that we wanted, then what you do is you take the optimal solution y star, and you take the subvector of that, being the first n components, and that will be a feasible solution to P. And then once you have a feasible solution to P, you can get a basic feasible solution of P, and that's that red asterisk implication that we had above. And I'm just asterisking it again and saying it takes some work to show how that's done. So we're just going to take for granted that we can go from a feasible solution to a basic feasible solution here. Yeah, and so these two cases being split up, giving us these two facts, that's following by that if and only if condition we just gave above. And that gives us the two-phase simplex method. So in phase one, you do what we've just said, and that'll generate a basic feasible solution to the linear program, or it will show that it's infeasible, or in other words, that it has no solution. So those are the two possibilities. And then assuming that you got a basic feasible solution from phase one, you use that basic feasible solution and feed it into phase two, being the simplex algorithm that we've already discussed in the prior video. And starting from that basic feasible solution in phase one, you generate either an optimal solution, or you show that your linear program is unbounded. Those are the two possibilities from phase two. So here's a tree diagram depicting that. So here's your linear program P that you start with. And in phase one, you go to one of these two branches. Either you're going to find out that your linear program is infeasible, or you're going to get a basic feasible solution. That's what phase one will do. And then in phase two, assuming that you went down this branch, you'll run phase two, and either you're going to get an optimal solution for the linear program P, or it's going to be you're going to find that it's unbounded, that it has arbitrarily good solutions. And that's what happens when you run these two, the overall two-phase simplex algorithm. And if you're keeping track, those are three outcomes that we could get: infeasible, unbounded, or optimal. And so that's actually a theorem. And it's so important. It's called the fundamental theorem of linear programming, FTLOP, or FTOLP. Three possible outcomes. That's what it's saying. The three possible outcomes of a linear program, for any linear program ever, they're either infeasible. Well, it's either infeasible, unbounded, or it has an optimal solution. Those are the three possible things, and exactly one of those will always happen. And that's just coming by this picture that we just drew. Now that's assuming some of the technical details that we've swept aside, but if you do assume those, and you can show that they are true after all, and then you can conclude this fundamental theorem of linear programming. So you might think that this is kind of obvious almost, like what else could have happened, so here's what doesn't happen. Well, for example, one thing that does not happen is that you have a linear program that has a supremum, but it will never attain it. That will never happen. So here's a very small, not linear program, here's a very small optimization problem. Max, just a single real variable x, and the constraint on it is that x is strictly positive and strictly less than 1. And that is not a linear program. But what's going to happen here is that you can see that the supremum value is 1, of course, but on the other hand, you're never going to attain it because you're always going to be approaching it. You're strictly less than 1. And that actually justifies why in linear programming we had always insisted that you never allow strict inequalities. You only let there be a less than or equal to, or greater than or equal to constraints. Those are the only types. And that avoids this situation where you have a supremum but never attain it. And so that guarantees that this fundamental theorem of linear programming is true. So that's why you always insist on less than or equal to constraints, not strict inequalities. Okay. So again, this is assuming those technical details. I'll come back to those details just one more time at the end of this video. But first, let's just do two examples, and we'll see both outcomes. So this is examples of phase one. So for the first example, we'll generate a basic feasible solution, and in the second example, we'll go down the other branch where we see that our original program P is infeasible. So let's do the first branch first. So here's an example that'll send us down that first branch. So here's the linear program, and it's just what it is. And then, by the way, take a look here. This component of B is negative, and so we said that we could always assume that all the components were non-negative, because if we're ever in the situation where a component is negative, just rewrite it so it has no negative entries. So just times by -1 for this bottom row here, and so -2, -9, 0, 3 becomes 2, 9, 0, -3, and then -13 becomes +13. It's the same linear program. So this is the real, quotes real linear program P here, where the B components are non-negative. And now you construct the auxiliary. And so how does that work? Well, it's the same matrix as it is right here, and now you've just appended the identity matrix. It's 2 rows, so it's a 2 by 2 identity matrix here to make dimensions fit, of course. And then this matrix times y equals the same vector b, 7, 13, and y is non-negative. And then what you're trying to minimize is the sum of those components of the vector y associated to these new columns that you've added on, associated to the identity matrix. So y5 plus y6. These are columns 5 and 6 here. So that's what we're trying to minimize, y5 plus y6. So we're this, typically when we do the simplex algorithm, by convention, that's supposed to be maximization, not minimization. So, but there's no problem there. Just rewrite min y5 plus y6 is max minus y5 minus y6. And it's the same exact thing, of course. So, so just rewrite it like that, and now run the simplex algorithm if that makes you more comfortable that way. But first you need a basic feasible solution before you run the simplex algorithm. What is that basic feasible solution? Well, the basis is 5, 6. It's associated to those new indices of the columns that we've added on here for the identity matrix, so 5 and 6. And the basic feasible solution is y bar here. So you take all zeros for the first 4 columns that you already had in the original, and then for the 2 new columns, 5 and 6, you take the components to be the components of b, so 7 and 13. So that's always what you do. So there's no work involved in that. We just get that automatically by how the auxiliary program is defined. And so now that we have our basic feasible solution, y bar, we can run the simplex algorithm on Q here to get an optimal solution. And if you were to do that, and we already know how to run the simplex algorithm now, we've formalized it and we did a video with an example, then what you get is what you would get is y star. The optimal solution is 2, 1, 0, 0, 0, 0. Well, it's an optimal solution, but it's the one that you get when you start with this basic feasible solution. Anyways, so this is an optimal solution that would come from simplex algorithm, and you can easily verify that this is optimal. You can check that it's feasible, of course, and then it's optimal because a lower bound is 0, and in fact we attain exactly 0 because each of the 2 components of 5 and 6 here are both zeros, and we were trying to minimize that sum of components 5 and 6, and of course we can't do better than 0 because y has to be non-negative, and but here we've gotten exactly 0. So y5 plus y6 is 0 plus 0, which is exactly 0, and so that means that this optimal solution for Q corresponds to the feasible solution of the original linear program P, where you take that solution X to be the first 4 components of this optimal solution for Q. So the first 4 components being 2, 1, 0, 0. So that's what this is. It's these 4 components, and so there you go. So that's a feasible solution, and so that means that the linear program P is feasible. And then by this mysterious implication that we haven't really discussed, you can then derive that P has a basic feasible solution. And in this case, you don't have to take that on faith. You can actually verify that, for example, a basic feasible solution is given here. So the basis being 1, 3, and this being a basic feasible solution. But in general, there's a way to get a basic feasible solution. And there you go. Now that you have your basic feasible solution for P, now you can run phase 2, simplex algorithm on the original program P that you cared about. Okay, so here's another example, and the other branch of that tree for phase 1 is what we'll go down this time. And so here's the example, and the components are non-negative, so we're already good there. And so you construct the auxiliary, and so it's min y4 plus y5, because there's only 3 columns right now, so you add on columns 4 and 5, corresponding to a 2 by 2 identity matrix that you add on here for the auxiliary, and it's 2 by 2 because there's 2 rows. That's what you're trying to minimize, y4 plus y5, and so the basic feasible solution here is, well, the basis is 4, 5, of course, and then the basic feasible solution is 3 zeros, 0, 0, 0 for the first 3 columns, and then for the latter 2 columns you do 1 and 5, corresponding to these 2 components. So 0, 0, 0, 1, 5 is your basic feasible solution for basis B being 4, 5. And now you have your basic feasible solution. Solve it with the simplex algorithm, and that'll give you an optimal solution. And in this case, what you would get is a y star to be 0, 0, 1, 0, 3. Now here, in contrast to the latter, in contrast to the first example, we're trying to minimize y4 plus y5, but here one of those components is non-zero, this one. So you get y4 plus y5 for this optimal solution here is 0 plus 3, which is positive. And so your optimal solution for Q, the auxiliaries, is positive, and so then that must mean that P is infeasible. Again, that's because if it wasn't infeasible, you'd be able to construct an optimal solution for Q, which is even better than this one, this y star, which would contradict optimality. So that must mean that P is infeasible. And yeah, that's how this process works. Phase 1 is pretty straightforward. So the unaddressed details, what are the things that we swept aside? So there's something that we swept aside in phase 1 and in phase 2. For phase 1, it's this implication of why is it that P having a feasible solution automatically implies that it has a basic feasible solution. So that's something that we're taking for granted. And the other thing that we're taking for granted is in phase 2, which is why is it that when we run simplex algorithm with Bland's rule, which is that convention of whenever there's multiple indices that satisfy a particular criterion, always take the smallest index possible. So that's the convention you use for the simplex algorithm. When you use that convention, why does that automatically imply finite termination? Or in other words, there's two corner cases that you eventually go down one of those two, which would be it would tell you either your program P is unbounded or it has an optimal solution. If there's no other outcomes that can occur, it'll definitely go into one of those two cases that were pre-specified. And that's what we're assuming. We're assuming that simplex algorithm with Bland's rule automatically implies that one of these two conditions will come out. And so that, assuming all these details are true, then that tree I drew above with the phase 1 and phase 2 stages, that's justified. And then that justifies the fundamental theorem of linear programming as well, which is that exactly one of those three outcomes, either infeasibility from phase 1 or unboundedness or optimality from phase 2, occurs. But we haven't addressed those details. We're just taking them for granted. But I just wanted to make it explicit that those, if you're thinking something's not quite right, we've skipped something, yes, you're right, we have skipped exactly those things. And those are technical asides, basically for a supplemental video. It's not really, I don't really want to consider, the next, quotes next video wouldn't be on those details because they're just kind of assumed within what we're already doing. It's more supplementary material that would justify these. So at some point I'll consider doing a supplemental video that addresses these things, just for completeness. But we can just assume those things and just get on with our lives, basically, for now, and to continue doing a logical progression of topics. And in fact, the next logical thing to talk about would be geometry, basically. How can we view all the algebra that we've been doing from a geometric perspective? So everything so far has been cast in terms of algorithms and algebra. What's happening in terms of visualizing things, in terms of, the dimension of space that we're working in. And in particular, what the simplex algorithm, what is that doing from a geometric perspective? So that's the next topic to address. But that will be for a later video. That's it for this video in the discussion of the first phase of simplex algorithm and combining those two phases, giving the overall two-phase simplex algorithm. So really cool stuff, but that's it for now. Thanks for watching.